Hello. Yeah, okay. So let's start the session. Yeah, okay. So let's start the session. So today we will be having assignment 5, previous year's assignment 5, and we will be trying to solve assignment 5, previous year's assignment 5. And so for analog circuits, which is NOC 23 EE19 code. So I will introduce myself. I am Vishakha Pandey. I'm PhD fourth year student from IIT Bombay. So let's start the session. Yeah, so let's start. Okay. So before starting the session, I would like you to have copy and pen with you so that you, meanwhile, we solving the paper, we solving the assignment. You solve the assignment before we give the solution to you, because when you solve the question yourself, you will get to know that what are your doubts for that question, and I believe that is a better and interactive way to solve a question. So all right, so I am hoping that you already have a pen and paper with you. So let's start the session. Meanwhile, if you while solving the question, if you get any problem, if you get any doubt, you can ask me while I am solving the question. Okay, so let's start. So this is the system given to us. Here the feedback is okay. So for question 1 and 2, there is some common data for question 1 and 2. So here the transfer function of the system is given as GS. The system is placed in a unity gain negative feedback as shown in figure 1. So this is the figure 1, and it is given that the gain of the system is 100 upon S into S plus 10 into S plus 10, and it has a feedback of unity. Alright, it has a negative feedback of unity, and so overall this is the system given to us, right? So now you have to calculate the phase crossover frequency of this system shown in figure 1. So phase crossover frequency basically means that the phase of the system at phase crossover frequency will will pass minus 180 degree. So something like, right? So when it will pass minus 180 degree, so that is the phase crossover frequency. Okay, is if we say that this is omega phase crossover frequency, then this value here will be, this is the phase curve, and this is the body plot of the system. Okay, so this will be minus 180. Okay, so now that I have given you, I have tried to make you understand the question. Now I want you to solve this question, and take 5 minutes and solve this question, and then we will discuss about its solution. Okay.
Hello,
Hello, Neeraj.
मैम।
Hi. Yeah, go ahead.
मैम, क्रॉस ओवर फ्रीक्वेंसी थोड़ा सा मतलब एक्सप्लेन कर दीजिए मैम।
अच्छा, तो
फेज
क्रॉस
क्रॉस
ओवर
ओवर।
फ्रीक्वेंसी, एक सेकंड। सो बेसिकली क्रॉस ओवर फ्रीक्वेंसी क्या होता है? क्रॉस ओवर फ्रीक्वेंसी मतलब कि हमारा जो फेज है, व्हेन आवर फेज गोज ओवर -80 degrees, like when it becomes less than -180 degrees, then the system as a whole becomes unstable. All right, so it is, see, from the name itself, it's a phase crossover frequency, isn't it? So phase crossover frequency is, uh, it's a phase which crosses over the frequency in such a way that the system becomes unstable. Are you getting my point? मतलब मेरा,
यस मैम।
हाँ, क्या होता है जब फेज जब इतना वो हो जाता है, -80 डिग्री से भी नीचे चला जाता है, तो उस टाइम पे हमारा सिस्टम अनस्टेबल हो जाता है और उसको ही हम फेज क्रॉसओवर फ्रीक्वेंसी बोलते हैं। ठीक है, समझे?
यस मैम।
हाँ,
जी जी।
okay. So now let's go and try to solve this question. So I hope I have also explained it in English. Am I right, Neeraj?
यस मैम, बोथ आर
हाँ,
कंफर्टेबल।
ठीक है. Okay, no, no. So I mean, since I'm recording the system, so recording this
यस।
session, so I want it to be in English as well. So, anyways, so I will go once again. So phase crossover frequency is a frequency when the phase goes over -180 degrees. So the exact frequency where the phase crosses -180 degrees. So this is the system, right? We have got that GS is 100 upon S into S plus 10 into S plus 10, right? That is S plus 10 square. So another thing that is given in the system is HS is equals to 1. That is, the feedback was something like this. This is G of S, right? This is the summation here, and so this, yeah, so the feedback is of unity gain, right? So omega p can be said as, it's a phase crossover frequency. Let's take omega p such that omega p is a phase crossover frequency. So at omega is equals to omega p, our phase of the system will become -180 degrees. So from here, can we find out the phase of the system? Yes, we can. Here it's a one pole at 0, that is -90 degree, and two poles at 10, so -2 into tan inverse omega by 10. Right? This is how we get the phase of a system. For for a pole at 0, we put -90, and for another poles we put like something like, as many poles are there, like 2 is there, the order of this pole is 2, right? So -2 tan inverse of omega by 10, right? This thing. So if it was 3, the power, the order was 3, then we would have put -3. If here it was 5, 4 or anything, we would have put the values accordingly. Okay, so this is how we find the phase. So here at omega is equals to omega p, we know that it's a phase crossover frequency, so the whole phase will be equals to -180 degree. So we'll equate -180 degree to this equation, which is -90 degree minus 2 into tan inverse. At the place of omega, it's omega p, because only at phase crossover frequency the overall frequency is -80 degrees, right? -180 degrees. So omega p by 10, and from here we'll solve the question, and tan inverse 10 45 degrees omega p by 10. So from here we got omega p is equals to 10, right? So this is simple arithmetic calculations, and you will get omega p is equals to 10. Do you have any doubt here?
नो मैम।
Okay, got it, right? What happened?
यस।
So now I want you to solve it for gain margin of the system shown in figure 1. Okay, so now what is gain margin? First, I want to tell you what gain margin is, right? So gain margin here is, see, uh, so we have the phase crossover frequency, right? So something like this is happening, phase is changing and phase becomes minus 180 degree here. So at minus 180 degree there will be some gain, right? So it will be known as gain margin. So what happens is, see, when the system at phase crossover frequency, when the system crosses minus 180 degree, the phase become, when the, sorry, when the system becomes unstable, the phase is lesser than 180 degree, minus 180 degree. So at phase crossover frequency, the phase of the system will be minus 180 degree, and when the phase of the system is minus 180 degree, for that frequency there is a gain, right? The gain of the system will be something. So now I want you to find this gain, and this gain is known as gain margin of the system. So I want you to solve for uh, for gain margin, where you already know what is the phase crossover frequency. So here phase of crossover frequency is 10 radians, right? And the system here is 100 upon s into s plus 10 into s plus 10. One second, I need to, yeah, 100. Okay, so now try to solve this question. I'm giving you 5 minutes, and solve this question and then we will discuss. किसी में गजब गजब नहीं बोला जाता है. दोनों मम्मी और आप दोनों बोल रहे हैं गजब गजब. You know how to solve for gain, right? So see, from here you can get mod GSHS, right? GH, let's put it like GH. Mod GH you can find. So for the omega is equals to omega p, you have to find out mod GH for gain margin. Here mod of GH you have to find. In this you already know the value of H, mod H, right? The value of mod H is how much? It's already, you know, it's 1. Now try to solve this question. I'll give you 3 more minutes and then we'll discuss. Chalo, let's start. So, you guys try to solve this question. Hello, did you guys try to solve this question? Hmm, no messages. Okay, all right. Chalo, let's try to solve this question by ourselves. So discuss the solution. Let's discuss the solution. So yeah, so we have to find gain margin. So here you already know the phase crossover frequency, which is equals to omega p. So here you have to find out GM, which is gain margin. So first you have to find out mod GH at omega is equals to omega p, and then uh, you have to find out gain margin. So gain, the formula for gain margin is 1 upon mod of GH at omega is equals to omega p. So this is the formula, and first you have to find out mod G of H. So at omega is equals to omega p. So you already know from the previous question that omega p is equals to 10, right? So we'll put that and we'll find mod of GH. So we'll put everything in this equation. So it's already, that is, in this equation, put omega is equals to omega p, that is 10. So put it here, and mod of GH will become how much? 100 divided by S. In term of S, it's when we find out the magnitude, we have put omega, and under root of omega square plus 10 square ka whole square, right? So this is how we find the magnitude of a system. So mod of GH is equals to 100 upon 10 into under root of 100 plus 100 whole square. So from here, we got mod of GH is equals to 1 by 20. So mod of GM will become 1 upon 1 by 20, that is the inverse of GH, which is equals to 20. So now that you have got this, you are supposed to find out the log term for GM. So since it in the question itself it is asked, yeah, see, it's in the options itself it was asked in dBs, right? The solution was given in dBs. So यहाँ पे dB में डालो, dB में convert कर दो ये value को. So that will be 20 log 20. So solve it and we got 26.07 dB. So this is 26.02 dB. Sorry, not 07, it's a 02 dB. Any doubt here? No?
No, ma'am.
Okay. Okay, great. So basically, see, from one thing that I want to tell you is, देखो, with the help of gain margin or the phase crossover frequency, what we get to know from this is the information that we able to find out using this gain margin value is that how much the system can be stable, right, with the um, gain becoming with how much system can be stable, like okay, gain margin in our terms you can understand that it's a quantity for the stability of the system. Okay, so as big a gain margin is, it means that as much the system will be stable. If gain margin is small, that means the system can be unstable very quickly. And if the gain margin is, let's say, infinity, that means that the system will always be stable. Okay, so now the next question, let's try to solve the next question here. So here it is written as Miller compensation is better compared to other compensations because it helps increase in phase margin with more reduction in unity gain bandwidth. So here it is saying, in the question it is saying that Miller compensation is such that it helps increase in phase margin So something like this is happening. So compensation, let's say, is happens, right? And it increases the phase margin. It increases the phase margin in total, right? But it has a reduction in unity gain bandwidth. So if this is the unity gain bandwidth, this is the bandwidth for the unity gain, then it is saying that with the Miller compensation, unity gain bandwidth reduces and the phase margin increases. So is this statement true or false? Try to intuitively try to solve this question and tell me.
False.
Yeah, false. Okay, very good. So why you think it is false?
Because ma'am, for this case, bandwidth, unity gain bandwidth should be increased.
Okay, okay, very good, very good. Now, why does unity gain bandwidth increases?
Uh, because of shifting the
Hmm,
poles,
hmm, very good.
uh, not poles, ma'am, because shifting the frequency means at that pole,
Hmm.
so we are getting the large bandwidth, so we can able to means control our system over the large range.
Hmm.
So that is the reason.
Okay, very good. What is your name?
Ma'am, Subham Guri.
Okay, Subham. So that's a very good understanding of Miller compensation, and good, Subham. So let's go and understand what Miller compensation is for other students. So see, huh. So for a simple compensation using simple pole shifting compensation using frequency, using sorry not frequency, using a shunt capacitor, what generally happens is, see, um, this is a system, let's say, right? And we know that if the system is in if the system has one pole, it will always be stable, right? But when the system goes from minus 40 degree, the phase can go above minus 180 degree. Now when the phase can go above minus 180 degree, it means that the system can become unstable. So uh, for uh, for a system which has more than two poles, the system can become unstable. All right. And so suppose, and how can we see that? When the gain of alpha beta is a closed loop. When the gain of the system becomes less than minus one, then uh, then it will become unstable, right? So here, till this point, that is when mod of a when mod of a is greater than 20 log 1 beta, that is 20 log 1 upon beta, because here, from here you can see uh, yeah, mod of a has to be less than 1 by beta, and in dB terms it will be 20 log 1 by beta to become unstable. Okay, so till the point where mod of a is greater than 20 log 1 by beta, the system is stable, which will come till here. Okay, so from here, fp2, the system can become unstable as soon as the phase goes over minus 180 degrees. Okay, so something from fp2, the system can become unstable. Now with the use of this shunt capacitor, this sorry so we know that till fp1, not till fp2. After fp2, the system can become unstable. Till fp1, we know that the system will be stable, right? It's going minus 20 dB, the slope is minus 20 dB. So we know that by till fp1 the system will be stable, and after fp2 the system can become unstable anytime, right? So with the use of this shunt capacitor, the system, the this fp1 shifts to fd, right? And from here itself, system will have a slope of minus 20 degree, and then here it will become minus 40 degree, and here it will be unity gain. It will have a till here the bandwidth will be there, right? Yeah. So earlier, with the use of this shunt capacitor, right, the we can see that the we have got stability. We have got stability till here, right? So from this point FD2 to FP2, we have got stability, which is more than uh, when it was from FP1 to FP2, right? So this means that okay, with the use of shunt capacitor, the frequency shifts till here, and we can have a longer stability, right? Earlier it was yeah. So earlier the stability was till here, right? Without the shunt capacitor, and now the stability is 1 second. 20 log 100. Yeah, this is 20. mm, yeah. So yeah, so stability has increased from only till here to here, right? It has increased. So this has due to the shunt capacitor, that is due to the pole shifting using the external shunt capacitor. But now you can see that the bandwidth, unity gain bandwidth, here the mod A is equals to 1, right? Here at this point, at this point the gain is equals to 1. So till here sorry, till here the bandwidth has decreased. That means that from here, earlier without the shunt capacitor, bandwidth was still here, the unity gain bandwidth, but now it has decreased to here because of the shunt capacitor that was added to the system. This means that the unity gain bandwidth decreased. So even for a simple shunt capacitor compensation, we know that okay, stability will increase, but the gain bandwidth will decrease. Now, what happens due to the Miller compensation? Due to the Miller compensation, something like this happens. So the something like this happens. Like so, the here we know that there 1 second. I can solve it here itself. So here we have FP1, right? Using the shunt, using Miller compensation, the new is new. There are two pole shifting happens. The first pole goes till here, and there is a new pole that FP2 also shifts to FP2 dash, something like this, right? So here, so earlier FP1 was there and FP2 was there, है ना? But now FP2, FP1 shifts to here, uh, not here. Let's make it like this. FP1 shifts to here and FP2 shifts to here. So thus our stability has increased, but the bandwidth has not decreased at all. Okay, getting? So something like this can be said, like there was two poles, है ना? One decides the stability of the system, other pole decides FP1, FP2, other pole decides the bandwidth. So with Miller compensation, this FP1 shifts to here and this fp2 shifts to here, and this fp1 shifts here. So the stability increases, and the the unity gain bandwidth does not decrease. So here Miller compensation is better because it helps increase in phase margin. This is correct, but it also, but there is no reduction in unity gain. No reduction in unity gain. Okay. So here the statement is false. The overall statement was false. Okay. Got it? Any doubt?
Ma'am,
Yes.
ma'am, in the lectures shared by professor,
Hmm.
their pole frequencies are given that 1 by GM R2 CF R1 means that the formula has not derived in the lectures, so we have to remember or just statements, just like statements, this type of statements we have to
You
remember.
see, it's a derivation, right? So unless it's a subjective question, you need to remember the derivation of the system. Otherwise, for competitive exams, you can remember the formula and directly solve the equation.
No, I am talking about the means the coming exam.
For the coming exam, for the assignment,
Not ma'am, the 26th March,
yeah,
that exam.
for that will also be mostly objective, it won't be subjective. So unless the exam is subjective, you don't need to worry about the derivation.
Okay, ma'am. No, means I am not worried about the derivation. I am worried about the means remembering the formula. I am
Acha.
telling you.
Yeah, so it's always better to have the formula handy, so that it won't take a lot of time for you to solve the question during exam time.
Okay, ma'am.
Okay. Any other doubt?